Hello, everyone, again. Brian Homerding, performance engineer. So I'm going to walk through the next programming models, which I'm going to cover both Kokkos and Raja. So before I do, I just want to touch a little bit more on something Thomas mentioned briefly, a couple of C++ features just to refresh you because they're kind of very important. They're how these programming layers are built. There's templates, which allow you to kind of parameterize your functions and things like that. So you can kind of specify a generic type name and be able to lower it down at compile time. So these portability layers, Kokkos and Raja, they're going to kind of go at compile time down to another programming model like CUDA, OpenMP, SYCL. And then the other important thing is lambdas, which are just kind of the way you construct a closure in C++, which gives you an unnamed function object. That's how you can kind of capture arbitrary code and then kind of move it around and invoke it in the underlying runtime. So first, I want to introduce Kokkos. So what is Kokkos? It started out at Sandia National Laboratory, but has developers at many different places. It's a C++ programming model for performance portability. As I mentioned, it's implemented as a template library. It sits on top of other programming models such as CUDA, OpenMP. So the kind of design idea here is that you have a single source and you kind of lower it down to whichever programming model is best supported for the target you're building for. It has a design standpoint to be descriptive, not prescriptive. Just going to kind of mention that because it's kind of one of the differences when you go from Raja and Kokkos. So in Kokkos, you're kind of describing the code, and then Kokkos is going to try to generate some good performance for you. Whereas in Raja, you're more prescriptive, saying, please break down my parallel execution exactly this way. Like C++, it aligns with the developments in the C++ standard, and it's a kind of modern programming solution. So you get your math libraries based on Kokkos and tools that are kind of built in with support for Kokkos. It's open source, you can find it on GitHub, and has many users across a wide range of institutions. So I mentioned the whole Kokkos ecosystem, which is pretty big and includes many things. For the remainder of the talk, I'm going to focus on the Kokkos core. That's your parallel execution and your parallel data structures. But alongside that, you have your tools for debugging, profiling, and tuning, along with your support with the tutorials, documentations, boot camps that are all available online. And then there's these Kokkos kernels, which are essentially interfaces into the math libraries or various other libraries. So the core abstractions, as I mentioned, there's data structures and parallel execution. So your data structures, basically, you kind of define a few different things inside here. So you have your memory spaces, which is going to define where your memory is going to live, whether it's on the HBM, the DDR, non-volatile, or scratch. Memory layout, so you can kind of control whether you want row or column major, if you want to do some strided accessing. And then finally, your memory traits, which is like how you access it, whether it's a streaming object, whether you want to do atomic accesses, or whether it's restricted. And then on the other side of it, connected with your data, is your actual parallel execution. So here you're going to specify your execution space. That's the where. So this is basically saying, oh, where do I want to run this? On the CPU, GPU, any other kind of accelerator that might be supported. Then you have your execution pattern. This is kind of the descriptive part of it. You're saying this is a parallel for loop. This is a parallel reduce, a parallel scan. This is a task spawn kind of parallelism. And then the execution policies, which define how to actually do that parallelism. So basically work over this range, break things down into teams, use a task graph. So there's a lot of core capabilities. I'm going to cover just a few of the kind of most important ones here and then mention a few later, just to give you an idea of the language and what you're kind of working with and what it looks like, and whether or not you might want to be interested in coming to the hands-on later today. So you have your parallel for, which is taking in a lambda. This looks pretty similar to some of the other models, and I'll go through an example after this. Parallel reduction, you have support for tightly nested loops, where you have kind of a three-dimensional array if you're iterating in your space. Non-tightly nested loops, in case you have some code that needs to execute in between two parallel loops or two arbitrary loops. You can build out task stags. Additionally, there's support for data, so your data allocation, your data transfer, including being able to do a deep copy. And then things like atomics and your various execution spaces. So OpenMP, that's if you want to run with multiple threads and then launch off to the GPU, you could be using CUDA. Moving to Aurora, there's support built on top of SYCL and OpenMP, so you have multiple choices. But this is just kind of touching the surface. There's a lot of other things supported. You have like offset views, sorts. You can have support for vectors, layouts right, layout left. You can do memory pools and profiling hooks. So there's really kind of a lot you can get into, but right now I just want to show you kind of what it's going to look like to write in this programming model, so you can get an idea if it's something you want to kind of experiment with and see if you like. So we're going to just do a simple data parallel loop, AXP. So it's pretty easy to express. Everybody can kind of go through the same example with the different programming models and understand it. So this ends up being bandwidth bound. So serial implementation, we're just loop iterating from 0 to n, performing our calculation. So this is a completely parallel loop. So in Kokkos, there's kind of a few different things. You'll notice that there's views being passed in here instead of just pure pointers. So that's where you're using your parallel data structures. These are things that Kokkos knows about. And then you have your parallel pattern. So this is a parallel 4, completely data parallel, able to split it up. There's this string label. This is part of kind of integration with the tools. This is because if you have ever programmed with C++ templating, when you get like a backtrace or a compiler error or something, you're going to get a massive, hundreds of characters template to try to figure out where you're coming from. So with this string, at least for the profilers and debugging, you can use it to kind of understand which kernel you're in without having to scan the very long string to figure out your kernel. Then you need to set your execution policy. This is very simple. We're just doing n iterations of this, 0 to n. And the iteration handle, so basically this is when it gets split up, how you're going to access into your space, your location in the iteration space. And then finally, you have the loop body, which looks the same as it does in the serial implementation, except now we're using the parentheses to access our views rather than the pointers that were passed in before. But this gets captured into a lambda, and that's how it gets lowered to the other backends. As mentioned with the other programming models, there's support for Kokkos kernels. This is like MKL, sparse graph kernels. There's built-in support for it, and it actually ends up being a little bit simpler to use them. This is because those views have some information stored inside of them, such as the stride and size information. So you just need to pass it the view, and it's able to kind of extract the size. You don't need to pass it along with it automatically. But otherwise, it's pretty much what you'd expect. It does kind of interact with the tools underneath. So it will try to internally call like one MKL or Kublas to use their underlying implementation that's optimized for the hardware. Then there's support for a variety of tools, such as profiling and auto-tuning, along with debugging and static analysis. Static analysis being pretty fun. It's some Clang tidy passes that basically understand the Kokkos semantics, so you can get some IDE integration and get some direct feedback as you're coding on what's going on. As I mentioned previously, it's used at a variety of laboratories, research centers, and universities. And I just want to post up here for everybody so you can find. The main thing is in the Kokkos GitHub, but there's various publications on it, recorded talks, and there's a Slack channel available if you want to join, just to be able to ask questions. Okay, now I'm going to jump over to Raja, which is another one of these ECP portability layers. So like Kokkos, it's built on top of these other programming models, with the goal being use the tool chain that's kind of working best for your device. So it's a library of C++ extractions that enable you to write portable single source kernels, and you compile them down for whichever device you're targeting at the time. So the main goal here is to encapsulate that application source code. So ideally your Raja application wouldn't need to change your kernel at all. You just kind of change the things around it, and then you use templates to specify how to lower things. It supports a variety of parallel patterns and performance tuning options. So performance tuning being one of the main things here is you kind of have control how to decompose your problem and how to like split up like block sizes you want to be using on CUDA and things like that. You have direct control over that in your execution policy. So it's kind of a double-edged sword. So you're able to do these tuning, but on the other side, you kind of have to do some of the specification. But it has support for everything you'd come to expect for kernel, like for parallel executions, such as reductions, scans, atomic operations. There's even data views for being able to kind of change how you're looking at the data. And then in your execution policy, you can do things like loop tiling and provide thread local data, or use the GPU shared memory. So really, again, for like the design standpoints and kind of seeing the difference between these two programming models. Raja is kind of meant to be incremental and selective. So you can kind of just pick this kernel, port that. It's fully interoperable with like the underlying programming model you compile down to. So if for whatever reason you do want to specialize one kernel, you could use like CUDA SIMD kind of intrinsics directly inside your Raja kernel, and it'll compile down to CUDA. Obviously, if you try to compile it down to SYCL, it's going to break. So all this, you kind of get a clean encapsulation, so you can have parameterized execution. So I'll go through an example and kind of see why this is. So you can kind of control how it executes without having to really touch it. So it's all put into a template, which you can put into a header file and include as you're going. So really quickly, this is one of the projects that's mainly reported to parallel execution. Alongside of it, there's some kind of related projects for memory, but then there's also like project templates to build it up. So it's kind of a separation of concerns type of project. So let me show you what simple loop execution looks like. So here, we're going to do a DAXP. So once again, we're going 0 to n. It's a data parallel kernel. We can run it completely in parallel. So we transform it, and now it's going to look pretty similar to you, hopefully at this point. So we're doing a Raja for all, so go over for all of them. We're taking an execution policy, and now we have this IT space, and then our Lambda, which again is specifying how do we access in our index space, or our iteration space. So you'll be able to kind of specify this. You can put these into a header file where you're using this execution policy. So for Polaris, you're going to be using like CUDA exec, whereas on Aurora, you might want to be using SYCL exec. Then you can specify your range segments that you're going to be using. And coming back to that design standpoint of totally encapsulated kernel code, we now have the same exact loop body being used in both places. So there's kind of 4 basic concepts that your loop execution has. That's your execution template, which is what is it? That's a for all. Execution policy type, that's the exec policy. The iteration space, you need to define basically how to iterate. This can be more than just 0 to n. This could be kind of arbitrary indexing. And then the loop body, which is a Lambda expression, which captures and lowers down. So as you can see here, we have our iteration space, and then our Lambda gets captured. The equals means capture by copy. So these execution policies that I've been talking about, I kind of mentioned it, but these can get specified. So it'll be using exec policy equals, and you can choose one of these. So say if we're running on Theta, which is a KNL machine, which you want to be using SIMD execution, you can be using SIMDX. Whereas if you go over to Polaris, you're going to want to use the CUDA execution, where you can specify a block size and whether or not it's going to be an asynchronous execution. Or you can use the OpenMP target support, which really you can utilize whatever you need to get the better performance on it. And this is kind of a simple example, but you can do some pretty complicated things, and you can do some loop transformations using these execution policies, some of which I'm going to get into later today in the hands-on. But for right now, just going to end with a couple of pointers again. This is available on GitHub, Raja, and the user guide kind of provides you a full list of features and supported backends. Thank you.
Thanks, Brian. Okay, we have time for one question while our next speaker is getting ready. Is there any question? I just want to point out this afternoon we will have breakout session for all of these programming models, so make sure to take advantage of that. You can either work on your code or just like attend the room and learn more about any of the programming models.